Okay, good. I think we're recording. So welcome to lecture 9 of NLP with deep learning. And today we're gonna be talking about so-called decoder-only models and basically the evolution of these general or pre-trained transform models, GPT so-called, which is one of the backbones of today's AI. So AI, these days, most people think about using LLMs for whatever, OpenAI, Gemini, things like that. So we're gonna be finally going to the core of today's AI, if you want to call it like that. You can call it language models if you want to call it like that. And there's more to that, but the core of that is based on the transformer models we talked about already. So we spend quite a significant time talking about the BERT model, the encoder model, which takes it takes a sequence and generates, learns or transforms the sequence of tokens into their embedding. So some representation which is useful for many things. So what can we use BERT for? Like there's things we can use the BERT for downstream. So what could be BERT used for? What can we use BERT for? We had something on the exercises, like, so what did we use BERT for? Yeah.
Text classification.
Yeah, like text classification. So how do you do this for text classification? How do you use the BERT model for text classification?
Text and
Yeah.
get output.
Sure. You input text and get output, of course, sure. But what exactly do you use for text classification? Like from the BERT model. If you remember this, there's, yes? Yeah, there is this first token called CLS, like classification token, which we add extra on top of, to the input, and we use the output of the CLS token to do some classification. What else? What else can we do with BERT? Except for classification, something else? Yeah. Yeah, so NLI is like two sentences, but it's sort of like classification because you stitch these two sequences to each other. You use the separator tokens, but you still use the CLS thing for classification. Yeah. Yes. Yeah, filling the gap is sort of like how we pre-train this thing. Like the model learns to pre-train itself, or like we pre-train the model such as like try to reconstruct the missing word. But like for downstream task, like whatever task we're gonna solve with these models, anything else except for text classification. If it were just text classification, it would be sort of boring model. But there's more. Yeah, no, I mean, I thought like more about sort of like sequence labeling thing, where you do like for each token you basically predict the class. So you can do like name entity recognition, part of speech tagging. Could be like question answering as well, where you try to find the beginning and end of the answer, for example. That's maybe what you mentioned. So these things, like basically conceptually two different tasks. One is text classification over the whole input or input sentences, and the other is sequence labeling. So this was like a sort of like a classifier on the sentence level and on the token level. Fair enough? Good. So this is great. This is great. And but there's some, I mean, not limitations, but this architecture is good for classification, but maybe not for other things. But let's recap the BERT thing. So what was that? We took the input sequences and run them through these input embeddings, which was the token embedding, the positional embedding, and the which part of the sequence that is first or second for BERT. But basically, the positional embedding and the token embedding are the important things. Then we run it through a couple of these transform encode layers. I don't know, 12 of them, 24 of them, and then the final layer. If we want to reconstruct the missing word, we would project it back to the vocabulary. And for each word in the input, the encoder produces contextualized word embeddings. Okay, good. So BERT is pre-trained with this mask language modeling. So basically, we mask a word or a couple of words. I think like 15%, not 15%, like even less. Oh yeah, I think it was like 15% of the words. We say like, okay, mask them with this mask token from the input, and by pre-training, try to guess which words were missing. So try to reconstruct, sort of like language modeling, like predicting the missing word. But So it seems like it's a language model, because in language model you get a sequence of tokens and try to predict the following token, like what's coming up after. But BERT is not designed to generate a text. So why cannot we use BERT for text generation? Why cannot BERT basically like generate text? If you give it an input, predict some output. Well, the thing is, any ideas why it can't predict text? Why it cannot generate text? Yeah.
Better representation from the context. So this was the thing we struggled with the word embeddings just in the matrix. So.
Yeah, it was. I mean, it's meant for representation of text, but the biggest issue why it can't actually predict, generate text is that we look. I mean, if you recall, like masking the tokens, where did we mask the tokens in the sequence? Like what did we try to predict from? So you have like decad set on the, and now we delete a word, let's say set, and we use the entire context to predict the word. So we are basically doing what? We are looking into the future. Like you're trying to predict this word, but in BERT, you take the entire sequence into account, so which means you're kind of conditioning not only on the past, but also on the future. And it's kind of, if you're trying to predict the next token, if you're trying to generate the next token, if you remember language models, like looking at the past token and trying to predict the next one, this is conceptually a different thing, because now we're looking into the future and the past. So the self-attention goes through all the context and looks into the future and the past and tries to reconstruct the word. And conceptually, you cannot use it for text generation. I mean, because there's only, for text generation, you have like some input, like the previous tokens, and you want to generate the next token. So you can only look to the past. So we have to, but there's basically an easy fix to do this, which is, which we'll be talking about today. So we want to turn this transfer model into a true language model, so to conditionally generate text. So if you recall what is a language model, we need to get a probability of, let's say, how should we call it? X, why not? X at position, let's say, k plus 1, equals to some word, given the sequence of A at position, X at position 1 equals to some token 1, X position 2 equals to some token 2, and so on up until X at position K equals to some token. So the conditional probability, we're conditioning on the left and try to generate the next word. And we want to build such a model using the transformer. Questions? Yeah.
Can we just use BERT masks the last word?
We can just mask the last word, sure. That will work. That would work. There's even better ways to do so. To take the advantage of the attention and not just masking the last word, but doing something more fundamental, which will help you like to I would say like learn more things at once. So let's jump into that. Your intuition is good. I mean, you could actually just mask the last word and try to run this model, and you would get some sort of this probability distribution. Yeah. Okay. Any other questions? So sound okay? So let's jump on that. So let's dig deeper into this self-attention thing in BERT. So this we call it unmasked self-attention, and this term will become very clear later in this lecture. Why? Because there will be something which is called masked, of course, the opposite of that. But why is that so? So this is a recap. So we take the input. This is a couple of rows for each word, and each row is the embedding of the word. So we are somewhere in the BERT model, in the transformer model, and for each input token we have some vector representation. So this is a matrix in terms of bunch of vectors. Okay, not as a matrix as a like planar projection. This is just a bunch of numbers. So the representation of the input. Okay, so far so good. And then we have these prediction to linear, to query key and value. So these are just some matrix multiplication, and we get these query key and value, which might have different dimensionalities now. And then we had this scale.product, so where we are basically taking each row by each row, multiply them together, we use it like Q times transpose key, and do this softmax and multiplying with the values. So why should we go through this again? Well, maybe we'll find something. So again, very ugly algorithm, but basically this is the same thing. So query, key, and values, taking the input, multiplying some weights and biases. So this is how we get this linear projections. And then this is the scaled attention, as I said, query multiplied by key transpose, which means you take a row from one matrix and multiply by a value from the other matrix, and it's basically like a dot product of two vectors in a way. And then you get this raw associations from that, which we scale. There's some scaling factor just for numerical stability. And then we run this over each row, run through softmax to get some probability distributions, which we use as a sort of like strength of attention from each token to every other token. I believe now the concept after 3 lectures and exercises is becoming a little bit more clear. I hope at least. Good. So this is it. So we have for a single query attention. So just if we take a single I have an example. Let me just skip this because this is not interesting right now. I don't know why I put it here. This is the same algorithm just over one row. So, but let's say an example. So we are at position 2. Okay, so the sequence is a couple of tokens, and we are at position 2 of our input. So I don't the cat, for example. And after a projection to Q, to the matrix Q, key, and V, we have our query at position 2 is just this vector, 11 and 12, whatever it means. So after some projection, we have a vector. And we have the following keys, which is K1, K2, and K3, right? Do you know where it's coming from? We have the query is a matrix, and we're taking at position 2. And the key is a matrix, which is a semi-dimensionality, and there are 3 entries: K1, K2, and K3. So this is coming after these, like these transformations. So we project into Q and key, and from that we take one row at position 2, which is the small q. Okay, good. Sorry, I skipped that, but now I hope you've clarified it. So, and this is an example. So we have the q is this, like, I don't know what these numbers means. I mean, these are not necessarily integers. These should be some real numbers, but I just put integers here for ease of computation on the slide. And it could be any real number, negative, positive, or whatever. We don't know what's in there, but some sort of numbers, okay? Just to make sure this should be real numbers, any real number. So we have the query, and then we have the keys, so which means so if we transpose the K matrix, we get these 3 vectors now as columns. So 1, 2 is the column here, 4, 5 is the second column here, 7, 8 is the third column here. And we can compute the dot products for the query, which each of these, or basically multiply this vector by this matrix to get the dot product. So let's take the first one. Q dot product with K1 is 11 times 1 plus 12 times 2, which is 35. Okay, so we computed this dot product. And analogically, it's basically row by matrix multiplication. Okay, I'm going very, very easily here. So the second one is again 11, 12 times the second row, which is 44 plus 60. Okay, some number, 104. Doesn't matter. And then we have 11 times this vector by this row, the dot product or a multiplication is 173. So this is the raw associations basically. This is what we get if you take the Q times key transposed is these 3 numbers, 1, 2, 3. Okay, now these are the sort of raw scores. So the raw scores are 35, 104, and 173. And now we're doing the softmaxing over rows. So what is the softmax of this vector? Well, I don't know. So how do you compute softmax again? How was that? What's the softmax? Yeah, go ahead.
Taking exponential of a single number.
Okay, of let's say 35.
Yeah, over the summation of the exponential of the.
So let's say exp, what is it, 35 plus exp 104 plus exp, what is it, 173, exactly. Yeah, and we do this for each of those. So, so now it's becoming obvious, like after this softmaxing, we get this vector of 3 numbers, and the first 2 ones are very small, and the last one is very high. Although the row associations are kind of sort of linear, but obviously we have the e to the power of this number here, so the exponential function. So big numbers become very big, and anything smaller becomes almost negligible. Like we're kind of normalizing, but normalizing in nonlinear way, in an exponential way. So now, okay. Now we have these three attention values, so to say. And remember, we are at position 2, and we have the attention values. This is for the attention for position 1, for position 2, and for position 3. So far, so good. Any questions? We just took one query at position 2 and multiplied by the keys and got some row associations, do softmaxing, and this gives us the attention value, which is the vector of these. We will then use them for weighting the value matrix. But here's the trick. So I mean, I'm just gonna repeat this on the next slide. So this is from the previous slide. And we end up with these 3 numbers here at position 2. And as you might see, the highest attention here is for the 3rd position. Like it means that at this position 2, whatever was the input, I don't know what the input was, but at position 2, the highest attention was to the 3rd token, which means the attention would be looking into the future. This is the problem we're having in this attention. Like everything attends to everything. So token from position 1 can have a strong association to token at position 64 or anything like in the future, and vice versa. So we're not limiting this attention, and this is kind of the issue. This is sort of like the transformer can look into the whole sequence. Like by design, the self-attention is associations of all tokens to all tokens, and as we see here, we might end up in this attention looking into the future token, and looking into the future doesn't work for language modeling. That's the problem we're trying to solve. Okay, so you see where the core of this issue looking into the future is, and that we can basically hack this in a way not to look into the future in the very core of this self-attention mechanism. This is the key of the transform. Is like there is a self-attention, every token looks to every token, and now we want sort of to attend, so this is attending to so-called attending to position 3 from position 2. And what we want, or what we wish to have, is that every token can attend to anything, but just in the past, not from the future. Questions? Yes?
In the end, we want to look at position 3,
so I'll show you an example on the next slide. Maybe it will answer your question.
okay.
So what we want is to attend, sort of look into only the previous tokens. So here we have an example with 4 tokens here. Okay, so some sentence with 4 tokens. So at position 1, we should not attend to token 2, 3, and 4. All right, we are position 1, and we shouldn't be attending or paying attention to or have any sort of information from the future tokens. At position 2, here, we should be able to look back. That's okay, because this is a previous token, but we shouldn't be looking into the future. At position 3, again, here, we should be able to take the information from the past, but we shouldn't be looking into the future. And if you are at the last token, of course, we can attend to every other token in the previous sequence. Does it answer your question in a way? Very, very well. So this is the problem we're trying to solve now. I mean, these are the row associations, right? Before we were talking about, we are at position 2, so we were taking the query for position 2 and doing the softmax over one single row. Like this example is basically just a single row at position 2 from this matrix. Now this is a global kind of view, so we have all these For all 4 tokens, we have these, we have the queries and keys. And so these are the raw associations after, let me just delete this. These are the raw associations after Q times key transposed. So it's a length times length matrix, like 4 tokens times 4 token matrix. Each token has some association with every other token. Okay, this is the association matrix. So what we need, so you understand the problem now. What we want to do is like not to look into the future in the self-attention thing. Everybody's with me? Sounds great. Cool. So we need somehow, because now we would be basically running softmax over this matrix for each row. So softmax of this row, softmax of this row, and so on. So 4 softmaxes over each row. All right, we take this as the input to the softmax, and then get the probabilities. So we want now somehow to, after the softmaxing, we want to have, basically these should be 0 probabilities. These should be all zeros, 0 probabilities. How can we do this in softmaxing? How can you tell softmax to end up with 0 probability? Any idea? So remember softmax, like we had a, so for example, softmax for this value would be exp11 over sum of exp over the row. Oh, this is horrible notation. I'm really sorry, but you understand what I mean. You know, we take all these items in the row and do this softmaxing. But now we want that all these are sort of ignored. So then, you know, the the softmax at position 2 should get 0. How can we get 0 from softmax?
I don't know, because the exponential function is converging to 0, so
Exponential function is converging to 0 where? So exponential function, this is it. So we're starting, you know, this is a good starting point. So what is actually the exponential function? It's something like at 0 it's 1, and then it goes like that and grows exponentially. So where it goes to 0? Okay, which means for it, it's converging to 0. So it goes to 0 at, fair enough.
so we should put in minus infinity.
Fair enough. So what happens if you put here minus infinity? Or you can define it's 0. You can say like, oh yeah, sure. I mean, you cannot work with a number unless you work with like extended real line and you really go fancy with all these kind of things, you know, minus infinity as a number. But you can say, of course, I mean, you know, it's converging or diverging to 0. Sorry, it's converging to 0 at minus infinity. You can say like limit is 0 at minus infinity. So if you put minus infinity here, mathematics won't get angry. And then you basically, what do you do here? No, sorry, this is a bad example. I mean, I'm not putting this here, but I want to put this, I need to put this at position 2. So for position 2, oh, maybe here we should put minus infinity, right? Like for all the future tokens, will it work? If I put here minus infinities, maybe it will work. And that's exactly, I mean, this is it. So what we are going to do is we replace, for each position, we replace the future tokens in this row association with minus infinity. No, you're good, you made it. Oh, yes, that's the intuition, exactly. Because we replace this with minus infinity, so which means now here, of course, after softmaxing, so let's say softmax, after softmaxing, you will get, I don't know, like this will be, what is it will be? This is interesting. What do we get after softmaxing this row? So it's gonna be, let's compute this. Let's do this, like exp of 11 over exp of 11 plus exp of minus infinity plus exp of minus infinity. Oh, my writing is really horrible, but yeah. So say again. Yeah, this is like okay. And this is 0, 0, 0. Oh yeah, sure, we get 1. Of course. I mean, it has to be a probability distribution. So this will be 3, 0, 1. So this will be like 1, 0, 0, 0. And of course, I mean, the probability distribution where you can attend to only one value will be like 100% attending to itself and 0 attending to the future. You were saying something?
Is there a specific reason that we're doing the stands with minus infinity instead of just pretending that the vector is smaller?
What do you mean? So how would you go about this? Like pretending the vector is smaller? Like what do you mean?
I'll probably just do a softmax over in the first row the first element, and in the second row of elements, and then just set the remaining elements.
Yes. So you can what you can do also, of course. So you know you want to end up with. Let me just delete this horrible thing. Oh, my handwriting is really bad. So what you want to end up is, for example, for this row, you want to end up with, I don't know, 0.2, 0.8, no, for the second row, 0.8 and 0 and 0. And you would say, oh, you know what? I'm taking just a softmax of these two rows, and then I get this and just fill it with zeros. Exactly. I mean, it's equivalent to the operation we're doing. But what's the reason? So think about this. You're doing right. So you would say for the first row, we do softmax here and then fill it zeros. For the second row, we took like 2 items and fill it with zeros. For the third row, we took 3 items and fill it zeros. This is equivalent to saying, oh, we fill it with minus infinity and run softmax over all rows. What will make a huge difference in one of these implementations? Think about it. Yes. No, I want him to think about it.
I'm kind of bothered by the minus infinity. I'm not sure whether implementing that is easy.
I can guarantee you, if you put torch minus infinity, you get minus infinity.
Yeah, no,
Because you put like you pay an extension. But what's the difference then? So you had an idea? Yeah, go ahead.
Matrix multiplication, so we're using GPUs, and you can do everything in just in one step, and you don't have to define anything complicated with filling something out.
Exactly. You don't have to define everything for each row differently and filling with numbers. You say the same operation will be used for each row in my matrix. And because of single instruction, multiple data, GPU paradigm, you can parallelize this very well. So basically, a single operation for each row, parallelized on GPUs, equals very fast. And it will make a difference. Like, you don't want to run a loop over, you know, the point is like, you don't want to run a for loop and filling stuff, although it's, you know, completely correct. You want to just speed up things as hell. So make it like, so I think, do you know this term like vectorizing some operations, like vectorization of operations? Maybe you've heard this. You want to vectorize everything as much as possible, which means you want to make everything, you know, run as like broadcasting or vectorizing. This is same concepts in a way. You want to make it run the same operation over multiple data as much as you can, because this will be parallelized by the hardware layer. This is why you fill in the very, you know, very, very ugly minus infinities in here. But it's the way it's implemented in Torch, for example, it's like exactly like that. Okay, everybody's with me with that? Filling in minus infinities? Well, that's great. So how are we going to do this exactly is masking. So why is it called masking? We basically say, excuse me. So now these numbers should be the minus infinities, and this should keep the same. So we're gonna create a sort of this binary matrix as a mask, which means everything which is 1 here will be, you know, we keep the numbers here under these ones. So like, you know, these will be, all these numbers will be multiplied by 1 as a mask, and not multiply. I mean, for these numbers, the mask will be 1, which means we'll keep the numbers. And for the rest, the mask will be 0, which means we're going to fill it with minus infinities. It's basically like sort of a NumPy version or PyTorch version of oh, here's a vector, and for all the entries corresponding to 1, keep the number, and for entries corresponding to 0, fill it with some other number. So like sort of like condition, but we'll do conditioning again not by if for each entry, but just, oh, here's a mask, and fill it either with some number or some other number. I hope we'll see the implementation today in the exercise or in one of the exercises, like how to do masking. So basically, and this is it. This is how you do like a masked self-attention. So you that's why it's called masked. You're masking the future tokens here in this row associations. And by masking means they will be replaced by minus infinity. Otherwise, they will stay the same. So I'm going to show this algorithm now. Again, so forget all this. We know everything up until here. And now what we're saying is for each tokens, which is in what is this T? Yeah, for all tokens, we're iterating through two dimensions of this matrix, number of tokens by number of tokens. If what does it mean? Oh, if this is 0, like not mask, whatever, so the mask is the matrix. Like if this is basically 0, then assign the minus infinity. Okay. I mean, now here we're iterating, we're iterating with the for loop, but basically what you would do in torch is just, there is an operation called, I think it's like torch mask. You would put a mask matrix and, if else. So it's vectorizing under the hood again. So it's very fast. And this is it. And then we just run the softmax over this to get, we get the zeros and we won't look into the future. Okay? Questions? Suggestions? So you discovered you discovered mask at attention. Congrats. And you discovered it too. And then if both of you were starting a company, you would get rich and you would. And I'm sorry, we are like, I don't know, 17, 16, 17, what year is 25? Time flies, we are 8 years too late. I'm very sorry. But it's good, I mean, finding out something which has been just 7 years ago, it's not a bad start, If you want to find something, let's get filter rich. That's great. Yeah, that's great. Yeah, we have. I mean, some people who are trying to get filter rich are not anymore in this lecture. So there was one guy, having a startup, in the first 2 lectures saying like, yeah, I'm gonna learn this, and I think now they're crunching numbers and customers. I think like getting filter rich, it's not just finding a good algorithm. By the way, what is OpenAI doing these days? I think they're just trying to monetize by advertisement, not AGI. I don't know. I don't read the news anymore. Like I don't read any news. I do, but like I'm not excited by the news like, oh, OpenAI is doing that and that and that, because it has nothing to do with research anymore. We'll get to this later, like the evolution of GPT. But this is the underlying mechanism of the mask self-attention, which means we attend only to previous tokens. Okay, this is good. So we basically, this is the depiction of this this algorithm again, and where we, after the scale.product, we just put the mask here. So this is sort of like operation. And it's in a way like an operation. If you look at this as a computational graph, which it is a computational graph, like every neural network is in a way a computational graph. We implement it as a computational graph. We don't think about it as a computational graph necessarily. You put a mask operation, which means, okay, you now have to do the only thing, like how you backpropagate it through the masking operation. It's very easy. So you implement a new function for masking. You implement 2 things, how to get a value out of this and how to compute the partial derivatives with respect to its input, and you're good. You plug it into your network and do backprop. Sounds easy. I think like once you do it just for real, then you will understand, oh yeah, it's just a function in a graph. So we can do backprop and learn all these parameters in all these layers, all these attention heads and stuff like that. Okay, good. So let's move on. So we solved the problem by this left to right masked self-attention. We solved the problem that now the output of, what is this? 1 to t. So all the outputs from 1 to t only depend, I think this is a typo here. It doesn't make any sense. No, it's true. No, I'm sorry. I'm confused by this notation. I'm sorry, but it's a slicing notation, but why I'm doing like 1 to t? I mean, basically, oh yeah, I see. So basically, we are conditioning on a sequence of 1 to t tokens, which means we can predict the next token t plus 1. So this means like we have a token 1, token 2, token 3, and after running the self-attention, we have some embeddings vectors for each of these tokens. And since they only could have looked into the past, like they are somehow through this self-attention, they learn the contextualized word embedding, but the contextualized word embedding is conditional only on the past. So we can use this for trying to predict what could be the next token, token 5. So we can use this for basically predicting if we get an embedding of token 5, which also depends on all the previous ones through the self-attention, we can say, oh, you know what? What this embedding, what is the meaning of this embedding? Which token it corresponds to? So we can just make a cut and try to learn it in such a way that the next token, sorry, the last embedding is trying to reconstruct the token which is missing here. If it doesn't make any sense, I'll show the algorithm in the next slide. But intuitively, you get all your input, all the embeddings for each of the input tokens, and then you can try to predict the next word. That's the idea. You're not trying to reconstruct the words in the middle as in the BERT encoder, but now we're basically only looking into the past to predict the future. Okay? Cool. So what is the forward pass? I mean, now we have a, basically it's a function. So we have a Decoder-only transformer as the general pre-trained transformers. I hope this is the right abbreviation. General pre-trained transformers, GPT. Generative pre-trained transformers. Are you 100% sure?
Yeah.
Generative pre-trained transformers, because they can generate text. Okay, not general. General makes no sense. Thank you very much. So generative pre-trained transformers. Now we understand why it's generative, because it's it generates text in a way that we will just show in a second. Pre-train means we pre-train it. We will talk about pre-training as well. And transformer, now we understand why transformer, because the transformer is the underlying architecture with the attention heads inside. So what we're going to do is that we have a input of token IDs. So this is the V star is the token IDs from the input. Then there's some bunch of parameters, like billions of them, 70 billions. And we have the output is a probability distribution over vocabulary. So each row of P is a distribution over vocabulary conditioned on the previous token. So basically this is the language modeling paradigm we're having. So it's giving the probability of token at position T plus 1 conditioned on the sequence of tokens from the past. So this is basically the sort of language model. If you recall n-gram language models, this is the same sort of paradigm we're using. Oh, what is the probability of seeing a word after seeing the previous words? In n-gram language models, we're cutting the input to using this Markov property, like only a few previous tokens, like 3 or 4. Otherwise, we couldn't estimate it. Now for transformers, we can take the whole input as well. All these, all tokens and the input, and run it through self-attention, through the forward pass to get this probability distribution. Or we could use, we are also talking about the recurrent neural networks, which also takes the whole input and try to predict the next token as well. So basically, the same paradigm, the same kind of model of, predict the next word, giving the previous words, you can solve it with many different models. N-gram models, good, but not perfect. RNNs, okay, great, but slow. Transformers, excellent, very fast. They do have limited context, of course. Like, there is a limited context of the size you can put in a transformer. And if you think about it, I mean, this is something which impacts maybe your lives, or maybe my lives, or everybody else using LLM. It's like, how big the context, like basically how much can you type into ChatGPT sort of thing, like how long the context could be, and it has a limit. So I don't know, like 16,000 tokens, 32,000 tokens, something like that. I mean, it's a huge thing, but you cannot just put the entire book in the context. It won't fit. So you have a limited kind of sort of input to the transformer. Okay, so this is the limitation, but it's a good limitation. I mean, you can overcome with better hardware. Like generally, this is the only thing that matters. Okay, so let's talk about a transformer decoder. Again, there's nothing fancy here. We have the input, push it through the input embeddings, so positional embeddings and token embeddings. Then a couple of layers of these transformer decoder. Inside of that is, we'll come to that, this self-attention. And the final layer is now, in GPT, there is always a final layer. So there is nothing like, oh, we just use the CLS token to predict something, or we just use a separation. There is nothing like that. We basically do like plain language modeling. For each token, we have a probability of being predicted given the past. This is it. So we just basically get a matrix of probabilities over vocabulary. The only thing GPT is doing is predicting probability of words conditioned on the previous words. There is no CLS token, no separation token, no classification, nothing like that. It's just a probability distribution over vocabulary. So it's a language model. And what are these transformer decoder layers? Is the same as we had before. So there's the input, multi-have self-attention. So there's a couple of these heads. For self-attention, we talked about the self-attention head before. And you remember layer normalization? What was that? Layer normalization. What is this doing? Okay. So we have let's say a vector x is, I don't know, minus 30, 100, minus 10. What is the normalization of this vector? What does it mean? You want standard deviation of 1 and mean of 0. So you take this number and center around 0. Okay, I cannot do this well, let's say after could be, I have no clue, something minus 0.2, 0.9, no, 2.9, minus 0.3, I have no clue. But the idea is like the vector got centralized, like the numbers are considered as a sample from standard normal, and they should have be centered around the mean at 0 and the standard deviation 1. So you just linearly cramping the numbers, close to 0 with some standard deviation. Good. So this is the layer. Yes. Yes.
Do we mask in every transformer decoder layer?
Yes. Every transformer layer, because if you don't mask, what you're doing if you don't mask?
Mix
You're looking into the future.
because the second transformer decoder layer is applied on the output of the first.
Yeah, that's right. But the thing is, okay, so the masking actually matters for training in a way. It matters for training. During training, you wanna, because in decoding, in generation, like if you do the forward pass, you put in all the tokens in here. So all the tokens like the, cat, set, they go here. And each of them will get an embedding. So this will be the cat, set will be 3 vectors, it's embeddings. And then they're run through this final layer to get probability distribution. So these are embeddings, final embeddings. And each of them goes to the final layer, which is projecting them into the vocabulary. So this is size of, I don't know, 1,000. This is size of your token vocabulary, which is 50,000, let's say, or 100,000. 100,000. Okay. All good? Do we understand this step? So we project here in the file layer, we project every word into probability distribution over vocabulary, which is from some small, dense representation of the embeddings, real numbers, to sort of one hot. We take from, not one hot, just a probability distribution. And which means here we would be, predicting basically nothing. This is the first token, but here we can use this for saying, oh, what is the probability of predicting the word cat after seeing after seeing this embedding, which is always conditioned on the previous embeddings, like during this self-attention. So here you're looking to the past, trying to predict the token. Here you're looking to the past, trying to predict the token. And of course, now if you reach this model, you can say, oh, what is the probability? No, excuse me. It's like generating always an expert. Like here it's saying, oh, use this embedding to try to predict an expert cat. So this is basically probability of cat given this is what you're trying to predict here. Here you're trying to predict the probability of set given the cat, and so on. So you reach the last token, and the question is like, oh, I'm trying to predict something. I'm trying to predict the new word, which is not in my data here. I'm trying to predict on, for example, the cat set on the mat. I don't know, something like I'm generating text, so I'm getting the probability distribution, and I can sample from the distribution to predict the next word. So the idea is you want to always look into the past, because if you start looking to the future, it will give no advantage of the model in the prediction of the next word. So that's why you put the masked attention in every head, every layer.
Use it in inference data to remove the mask, because for words like in the middle of the sentence, sometimes context from the future of the context that we put in is important. So, for example, the cat that is red, and then we try to predict the
Yeah, sure. I get it. No, so you're asking like, this sort of left to right, is it important? So if I understand your question right, you're saying I'm trying to predict the next word here, which is unknown. I'm trying to generate the next word. But it means in this embedding, I have all the information from the entire context. I have everything in there. And the property of that is like, yeah, of course, this is the entire sequence from all the embeddings. This is the entire sequence until this point, and this is until this point. So basically, each step is adding new piece of information. But at the end of the day, you have the full context, which is what you need for predicting the next word. Okay? Yeah, you keep the mask in there, of course. You keep the mask because you don't want to make a difference between like what you're training. Like basically would be sort of like changing the architecture in a way, and you want to keep the architecture for pre-training and inference the same because, well, is there a reason for changing the architecture? I don't think so. I mean, there's a question like whether if you remove the mask, what the impact would be on inference. I think the cool way is just to take GPT. Hack not hack, like change the mask in the attention head. Maybe there's even like in the implementation there's a flag just to unmask. Run this and see the results. So maybe somebody tried. I'm not aware of this, but there's billions of papers on that. Does it answer your question? Okay, cool. Any other questions? Okay, so let's look into where are we? Yes, here. So now, for each of these transformer layers, we do layer normalization first, then we run it through this several heads of self-attention, and then we do a summation with this sort of like, I think it's a residual connection. So residual connection. So this is the first part. And the second part, again, layer normalization, and it runs through another feed forward or NLP, and again, residual connection. This is the same as in BERT. The only difference to BERT is that in BERT, I think we had the layer normalization after summation, and I think that's pretty much it. Like it's almost the same. So GPT is almost the same as BERT. There's not many differences. Okay, so the full algorithm for decoding on the transformer for the forward pass is this one. Which summarizes the whole picture in like one algorithm. So if you wanna, the difference, like there's all these dimensions are mentioned here, and they should kind of match. If you implement it, and you need to know which parameters are there and stuff like that. But I'm not going to talk about this algorithm because we had this on this depiction already. So as I said, like the differences from BERT forward pass is like we switch the ordering of layer normalization. So now it's before going through the self-attention, and there's no final layer projection because we just use these, we don't project, well, there's no final projection. We keep sort of the same matrix or the same rows of embeddings from layer to layer. And after the last layer, we do the projection to the vocabulary. This is the only direction. And of course, the biggest difference is the left to right masking for BERT. Left to right masking for GPT, for the decoder-only transformer, in contrast to the masking in between for BERT. Okay, good. Any other questions and clarities on how the self-attention, mask self-attention works, or how GPT kind of the forward pass works? We're good, more or less. Okay, so let's talk about training. So how do we train this model? I mean, any guesses? How did we train BERT? How did we pre-train BERT? So we used, and this is interesting. So we use BERT for text classification, sequence labeling, and things like that. But we pre-train it with the gap filling, sort of. So we have a different task for pre-training and different tasks sort of for the final tasks. These are different things, right? I mean, filling the missing word is different from text classification. So their pre-training objective was different. The GPT will be pre-trained in the same way it's used for inference, just language modeling. Just always try to predict the next word. This is what we are going to pre-train. So there is no like, oh, is this sequence before the second sequence, or what is the there was missing word in the middle? No, always like, oh, what is the next word giving all the previous words? So, and this is how we pre-train it, and this is how we use it. Like, oh, given a sequence of words, give me the next word. So this is like a single objective for pre-training or fine-tuning. If you're going to pre-train or fine-tune a GPT model, you're doing essentially the same thing. It's a language modeling task, only language modeling task. No kind of fine-tuning on classification. So if you just use the CLS head or whatever, there's no such thing like that. Plain language modeling. And the algorithm for training this model is also always stochastic gradient descent, or we're using backprop for finding, using backprop for finding the gradients. So we have some data points. Again, we're running through epochs. We have running through a number of data in each epoch, and we're taking an example xn, so which is bunch of tokens. We run it through the transformer. We run it through the decoder transformer, basically through all these layers, to get the final projection matrix. So this is the matrix which project each word back into the vocabulary. And oh, this is interesting. So we're computing the loss, and does this ring a bell? So we have a minus, sum, and some logarithm of probabilities. This is some sort of cross entropy, and this is cross entropy basically. But there's an interesting thing. So t equals 1 to L minus 1, and then these indexing. So we'll look into this in detail to understand this exactly. But so we compute basically the loss of the final whatever after the entire sequence. There is a loss. What is sort of the domain of loss function? So what is a loss? What are you getting out of the loss? Is it a vector? Is it a matrix? Is it something else? What is the loss? Say again? It's a real number. Anything else? Any real number? So you're asking or answering? No, I mean, so it's a positive real number, exactly. So the loss has to be some real number which is greater than 0. The smaller the loss, the closer to 0, the better it kind of fits the training data. So you were right. Cool, okay. So we get a loss, and what is this thing? That's a gradient, exactly. What is this thing? This is the learning rate. So we're updating all the parameters by taking the gradient of the loss function, which means all these partial derivatives with respect to all these parameters, like the 70 billion parameters, multiplied by learning rate and subtract from the existing parameters to get the next parameters. The weights, biases, everything in the network. This is a gradient descent or stochastic gradient descent. You take an example, run the loss and whatever. There's no batches here, so you can make it work in like mini batches, if you will, by just simply parallelizing the whole thing. But this is just a standard algorithm we've been talking about like the whole course. Okay, so the question now is, all good? Like training by stochastic gradient descent and backprop, cool. So let's look at these negative log likelihood, aka cross entropy loss here. So we have an example here. The cat set, okay, so we transform this into 3 numbers. What are these numbers again? Yeah. Not really. This is just, so each word corresponds to a number. What are these numbers first? Yeah. Yeah, exactly. This is just the index in, how do we call it? V, token, vocabulary is for token. Say again? Dictionary? Token dictionary? Yes. I had a different word which I forgot. So let's call it token dictionary. Okay. Token dictionary, vocabulary. There's another word which I forgot. Anyways, so these are the token indices. We run it through the transformer. And after the last layer and projecting to vocabulary, again, we get this matrix. So again, a sanity check. What is this number corresponding to? The size? Sorry, the dimension, like how many rows do we have here? No. Yes. 3 tokens. 3 tokens. Each token gets its own embedding and then projected to vocabulary. Good? Now you can answer your now you can use your answer for the other question. What's the dimensionality of that? This is the size of the token dictionary V, and this is the size of the V. Yes, exactly. And what else can we say about this? For example, each row, we sum it up, we get 1. Why? Exactly. This because we design it such a way like it has to be a probability distribution of the vocabulary, so it has to sum up to 1. Very well. Everybody's with me, so sanity check. Like if there's a matrix, we should understand what it means and what's inside and how big is that and what is this. So we clarify that. That's great. So we have this matrix, and now let's say we are at position 1. So this is during training. Remember, this is during training. So we're trying to get a loss of this thing, and we are at position 1. So this basically corresponds to this corresponds to position 1, for which we get this sort of prediction after running through the decoder layers and everything, after the last layer for projecting the vocabulary. And these are some numbers, mostly zeros, close to 0, and at position 11,987, we got some number. So this is interesting, because now for T1, so we are at position 1, and the model should learn to predict the next word, right? We are at position 1, and the model should learn how to predict the next word, which is cat. You with me? For anything we are at, we're trying to predict the next word. So we are position 1, which is and we're trying to predict or reconstruct or learn how to predict the next word, which is cat. And the cat index is 11,987. So this is the cat, the cat set. So of the embedding of this first word, which is turned into the probability distribution over vocabularies, we're trying to predict what is the word that the word should have been cat, like the next word. And that's why I highlighted this position here from this matrix at this position of the cat. Okay, what is the gold label now? I mean, so loss, basically, a cross-entropy loss takes the sort of like gold standard data, which is the one-hot encoding of the target word, which is one-hot encoding of what?
The word we want to predict, so at the position we.
Which word?
The third, second position. So
Which is? It's one-hot of cat, exactly. So this is what you're trying to predict, and this is just one-hot representation of the next word, cat. And so this is gold label, and our sort of prediction is this row, which is, so we have two vectors now. Okay, so we have the gold vector, and we have or we can take this as probability distribution, and we have the prediction. And now if you just run cross-entropy on these two vectors, is it exactly what you get a loss? This is exactly how it is. But we can actually simplify it, not just, this is the categorical cross-entropy. If you run this on these two vectors, you get the answer, you get the loss. Okay, categorical cross-entropy it's like multi-class classification problem. You're classifying a vector into 100,000 classes, which is the same thing as trying to predict the next word, right? I mean, this is why it's classification in a way. So we can run it through this cross-entropy loss, but we can simplify things. Basically, if we run this through cross-entropy, we would have to look into all these positions from 1 to, 100,000. But if you look at position 1 to 100,000, all of them are zeros except for the position where, of the index of the predicted word. So we're going basically to ignore all these zeros and just pick the value at position which corresponds to the 1, like that. We just care about the position 11,987 because this is where some information is. Everything else should be 0, so we save some compute by not multiplying by zeros. So far so good? Okay. So we get basically a log of this number, which we turn into, negative, sorry. Never forget the minus. Negative log of, now we're saying, take the first row and the position 11 whatever, which corresponds to take the first row and, you know what? I don't know what number is, but we can generalize it. Take the input and, this should be t, I'm sorry. And take the t plus 1 position. Okay, t is 1, so we are at this position, and here we should look at the index of the next position. Okay, this is 11,987, which is exactly where we find the number which we are interested in. And we can generalize into, for any generic t, this is correct, this was 1, t equals 1, and we generalize it to this very kind of generic cross-entropy loss, where this is like explaining these indices into the P matrix. But if you work it backwards, you end up with a categorical cross-entropy, which you understand from classification already. So there is no magic. It's just a standard cross-entropy loss, categorical cross-entropy loss. But we are saving some time in just ignoring all the zeros and just doing some indexing. So if you see it, if you see this implemented in Torch, you will see just indexing of matrices. Why? It's just super fast to do indexing matrices is just fast. There is no for loops, nothing like that. You just put the index to the matrix and you get a number. Okay? Does it make sense? To some extent? Categorical cross-entropy loss is a standard thing, like for classification, and we're using this for, trying to reconstruct or trying to predict the next word or try to learn the next word. And we do this, so if I just come back to the algorithm, we gave this example for t at position 1, but obviously, we do this for all positions, we do this for all positions from 1 to L minus 1. So for each token, like the cat set on the mat, here we're trying to predict cat, here trying to predict set, and so on. And so this is t equals 1, and here t equals L minus 1, because all of them are L. Here we're trying to predict met. And of course, here by training, we're predicting nothing for the last token because there is no information. We don't know what's coming next. So this is for training this language model. So and this is interesting. Now we are like, you take a sequence, just throw it in, and the loss is basically summing up all of these predictions at once. So you're trying to predict the next word for each sequence, even for sequence of length 1, sequence of length 2, 3, 4, and up until sequence of your maximum context. For each of those, you're trying to predict the next word. So the network is trying to learn, even like predicting from a single word, predict the next word, or even from 2 words. Yes?
But we are putting in just a whole sequence and predicting the last word, and we don't always look at the particular.
No, this is training. This is training. This is how you train the model. Yeah.
My idea was, okay, we have I don't know 100 tokens,
Mm-hmm.
and it would be a waste of data if we would just predict the last token. So
Exactly.
Take the whole thing. Okay, so we chunk the sequence and put in every substring.
No. It's no. You don't put in all the substrings, because basically, if you put in a sequence of the cat set and so on, like the full context. So like if the transformer input maximum length would be like if max L is 5,000, you would put 5,000 tokens here. So this would be like 5,000. And then it will immediately learn for each length automatically here. It would learn what is the prediction after seeing 1 token, after seeing 2 tokens, after seeing 3 tokens, after seeing 4 tokens. But you don't do it like, by chunking this. It's done automatically because you have all these words already as the input, and for each of these words, you run it through the decoder layers. There's this masked attention, which means every token from your sequence will look only back, and you're trying to reconstruct the next word for each, at each position.
And this is the reason why we sum up all the entities.
Yeah, you sum them up, exactly. You sum them up. I mean, otherwise you would have like, for each position you would have a different loss, and you sum them up, because minimizing the sum of things sort of is also making sure that you're minimizing at least some of those. You're minimizing the sum of the losses, yes. I think you could even take a, no, sorry, wait a second. Yes, no, that's why you sum it up, yes.
But just all at once.
You actually look at every probability for each substring, exactly. Each like left to right substring, you're looking at the probability of that. But you sum these losses together and just do the backprop at once for the whole network. Yeah. I think you could actually here do like an average. You do like average loss, but summing them up is the easiest thing to do. Yeah. Okay, that's a great point like to discuss. So basically you're learning the model for all sequence lengths at once, for length 1, length 2, up until length maximum, like, I don't know, 5,000 or something.
And the other thing I was asking myself is, so we take care that it's always the maximum length.
For training, you always take care there is a maximum length.
Okay, so it would make sense to put empty tokens in it, because we wouldn't train all the parameters. But at the same point, I was thinking about, okay, if we don't put in empty tokens, so how can the model then handle empty tokens? And it's kind of okay, we don't actually train the last substring on empty tokens.
Oh, okay, interesting. So I see. So you're saying, okay, where for training we put as long context as we can and no padding, so there's no zeros anywhere. We just take the maximum sequence, because it should learn as, we will be wasting resources just putting like shorter sequences. But your question is like, when do we do inference? and we start with like a shorter sequence, how does the model handles like the zeros or whatever? We don't look into the future, and then in inference you would say, okay, I mean I'm prompting with a shorter context, so start predicting the next word at the position before you hit the padding, the zeros, something like that. The exact implementation is a little bit trickier in GPT, and I guess we have something in the exercises to actually like looking into this shorter context than the full context. Yeah, but I think your reasoning is makes sense. Yeah, thanks for these questions. Any other questions? Okay. So we are here. We are here. Prompting. Yeah. Okay. So this is what we kind of discussed already. So we have the input. Now this is sort of like decoding or like generating the text finally. We have the pre-trained model, we pre-trained it with language modeling, and now we want to do inference. So we have some input, which is a prompt, and everybody these days knows what a prompt is, like whatever you type into GPT or whatever. So we turn it into a sequence of token IDs, and what we want is some other sequence of tokens, which is a continuation. And there is no magic in there, so we run the transformer for the whole input, and here, predict the probability distribution for the next token. So this is how we look up into the matrix which token we need to, basically the last sort of last token embedding, which should predict the next token, and we get a probability distribution. So this is what we did before. And then from this probability distribution, we sample token from this probability distribution. So what does it mean? We have a probability distribution, say, so this is a vector of, let's say, 100,000, which is the size of the vocabulary. Token inventory, now I remember the term, token inventory, somebody's using as well. And this is a probability distribution like 0.001, 0.0001, 0.02, and so on and so on. And we are going to, so we need to turn this into, each of those corresponds to some token in the inventory. So for example, this could be A, this could be D, this could be, I don't know, some of those. And these are probabilities which which word should be predicted from this probability distribution. Which one are you going to take? So we can take the maximum probability token. And I think it's called, if I'm not mistaken, greedy decoding. Greedy meaning you're greedy and taking always the maximum. Like if you're greedy, you always take the, you want to take as much as you can, right? I mean, the meaning of the word. The problem with greedy decoding is it kind of sucks. Like, the generated text by greedy decoding is very repetitive because it always takes the most probable continuation of the sequence, like the most likely. So it's going to be usually like, empirically, it's going to talk about either repeat the word the very many times because this will be like the most likely word to continue sometimes, or it's going to, just do phrases which are completely not meaningless, but just very useful phrases like I am, you are, and so on. So the greedy decoding is kind of bad. And so what you're going to do instead is not to take the maximum value, but to sample from this distribution. And I think we talked about sampling already, but you can basically say, draw me a number, draw me a index according to this probability distribution. So you can get anything, depending on the probabilities. Or you can say, sample from only like the top 100 probabilities or top 5 probabilities. And this is where the randomness in decoding and in any language modeling use, like, if you run the same thing in GPT, like on different places, different times, you will get different answers. And the reason for that is that we are not using greedy decoding, we're using random sampling from this probability distribution. And of course, we are also changing the parameter here of, we're changing the distribution a little bit because we're sort of multiplying this or, putting that to the power of something. 1 over tau. Do you know what that means? The tau thing?
Temperature?
That's the temperature. And then you can understand the higher the temperature here, the more uniform this probability will come, which means the more sort of random. The lower the temperature, the more spiky it gets, and then it, with very small temperature, you get basically to greedy decoding, because there is only like one item which has super high probability and they all are almost zero. So the temperature parameter helps you to kind of control the randomness of the sampling. And I believe in some APIs to some even closed models, you can actually tune the temperature to get more like I don't know, like more random answers. They call it like more. If you go to LinkedIn, it's like more creative answers with these temperatures, and these temperatures like more. I don't know. It's like a bullshit in a way, because you know what it means. You're basically turning a knob on the probability distribution and changing the probability distribution to make it more uniform, less uniform, and you're sampling from the distribution, either taking the full distribution or taking like the max top K values from this distribution and sampling from these birds. This is how it works under the hood. Okay.
I have a question. I'm confused a little bit on how the GPT model knows when to stop the output. I understand that it has maximum output length.
Yes, when it stops.
Yeah.
Well, how would you do this? How would you fix that? It's very easy to fix. I guess this is how it works. I don't know. Actually, it's a good question. Any idea? So you want to be rich. So you had a chance already. So your turn.
I add a special token that signifies this is the end.
Yeah, but it could then use it every time. You know what I mean? I mean, it will start and choose it every time. Huh? It will choose it every time. It wouldn't choose it every time, but when it will choose it, then it will like produce an output just ending immediately.
Yeah.
I have never seen happening something like that.
Yeah, because it's not a stupid model in a way. Like it knows when to stop somehow. Like after a meaningful phrase, there should be end of it. So it basically, yes. I mean, I think you're right. I think exactly there is like end of sequence token.
Yeah.
It generates end of sequence, and you stop decoding. How the model knows when to stop, and knowing means like, oh, there's some agency, like the model answered my question, know how to whatever, like this is the end of information it's giving to me. It's a different story. Like how do you make it work? Like why it works in the first place? Like how the hell it works? Like how the hell is like, yeah.
Isn't it like when we are training the model also train to know when an answer will end, or this is the full information?
Exactly. Yeah. I mean, you can fine tune it on some task, and by fine tuning on the task, it knows like when to stop generating, because you say, oh, the answer. I mean, let's put like very easy task is machine translation. You say, oh, translate a sentence something into some other sentence, and of course there's different lengths of these sentences, like in both languages. So, but you're giving a signal to the model, like if it generates, so you reach the end of sequence. So the next token being predicted should be end of sequence, and the model predicts something else. What does it mean? You penalize the model through the loss function, saying like, no, you should have stopped here. It should have been end of sequence token, but you generated something else. So the model learns when to end in the same manner as it learns how to generate the next token. Basically, the end of sequence is a sort of the next token to be generated, and it has to learn as well. Does it answer your question?
I think what I'm thinking about is that every time we teach model something, so we input just information.
Yes.
And it has like a maximum context. And I have a feeling that the information that we give to the model is always bigger than.
Oh, okay. I see. I might have an answer to this. So this is the way. So if you just pre-train the model, like GPT model, if you just pre-train it on just raw text and do the language modeling, it's gonna be useless. It's gonna be a language model. So whatever you type in, like if you do like machine translation and type it in, it's just coming like it will be continuation of the sequence. It will just continue spitting out the sort of continuing the input, because this is what it knows. It's only trained to fill in, to continue generating the text. So what you do then is you start fine-tuning it for a special task. Exactly. Or these were like the early models of GPT, or Then you introduce like this reinforcement learning from human feedback, which is a different story. We'll be talking about this like in the next lectures, okay? So far, it's a stupid language model. It just, continues the thing. When stop generating, it's a special token end of sequence. I'm almost 99% sure, but not 100% sure. So, I would need to check this. Yeah, okay, cool. So let's talk quickly about the evolution of GPT. Yes, you have, sorry, go ahead. Yes.
Now we just use the last one, don't we do unnecessary computation
in the training, in the inference?
Because the model learned to predict all the probability distributions.
Oh yeah, okay. So you're saying, oh, we're actually producing the full matrix P, but we're looking in the last row of these P anyways. It might be, there's some unnecessary operation in a way you're not using the other preceding token embeddings or token predictions. You just take the last one. You are right. I think there's some wasting of computation, but it doesn't matter because it's all parallelized anyways. Like you get all these things at parallel. So I don't think, maybe you can just bypass that if you want. I don't know. I really don't know. You are right. Like conceptually, you don't need all these embeddings. For all these words, you need just the last one, but maybe there's a trick to it. I mean, I'm pretty sure like there's like tons of papers from 2020 doing like how to speed up things in inference and stuff like that. So I don't know, to be honest. Okay, so let's move on to evolution GPT. So the first thing, okay, so how like GPT now is a thing, like it's powering all these all the AI hype, billions of dollars, and who knows what's. The world is changing in a way nobody knows. But how it started, it was the first GPT-1 model back in 2018. So it was, I guess, this one in the ICLR conference in Vancouver. And basically, the GPT model is based on the very famous paper by Vaswani, Shazir, Parmar, Uskorza, Jones, Gomez, Kaiser, and Polushkin from 2017. So this is the attention is all you need paper, which is like, billion citations today. Where in this paper, so the task they were interested in is sequence to sequence thing, like machine translation. So the first transform models were basically tested on machine translation. And what they proposed in this paper was basically BERT and GPT at once. So it was like encoder, decoder. So they took the BERT model, which is the full cross attention, like from encoding the whole sequence, and which took the input sequence to be translated and learn the representation, and then the decoder model, which is this masked attention, which we talked about today. And there were some connections of those on these, between these attention layers. So it was a very complicated model. You had an encoder on one side, the decoder on one side, and it worked. It worked well. The architecture was kind of promising, and people took it and just say, oh, you know what? Let's take just the encoder model for BERT, for classification or sequence labeling. And the other stream of research was like, oh, let's take it just for generation, just the decoder model, like a language model. Let's ditch the part of encoder and just take the decoder as GPT. And the first GPT papers showed up in around 2018, a year after in the same era as the transformer was introduced. And the task they were doing this here was generating Wikipedia by summarizing long sequences. It was a text generation task, and what they did. So Alex Radford, the last author, Ilya Sutskever, I cannot pronounce his name, and they adapted the decoder-only transformer and trained it as a language model. So this is what we did: like predict the next token, predict the next token, predict the next token. No, nothing else. And they fine-tuned with an extra final layer for the given task. So you could use this and put put a final layer on whatever you're going to do. And they improved the state of the art on 9 of 12 data sets they studied. So I don't exactly recall all these tasks they were studying, but it was like language understanding. And what they used for pre-training was a book corpus, 7,000 unique unpublished books. So it's a very small corpus. Like, think about this, 7,000 books. I think it's even something you can put in like in a library here, like physically. 7,000 books would fill this room maybe or not. It's very little data. Their model was 12 decoder layers. So, the transformer decoder layer 1 until 12. And each of them had like 12 attention heads in parallel. And the embedding size of some of these numbers, whatever, doesn't matter these days. But there were some numbers, and I think like it took some time to train this model and to fine tune. Was the evolution? They get state of the art results on some of these data sets, but it wasn't like, oh, now the world has changed. Like, it wasn't. We weren't there yet. Then it came GPT-2, which is a bigger GPT model, larger, and the same. You basically make it just bigger by throwing more hardware. 48 decoder layers as compared to 12, so really making bigger size. And 16,000 size of the embeddings. So the number of trainable parameters grows over 1 billion already. And back then it was considered like, oh, this is a big model actually, like back in 2019. So these models became more capable, and also like they train it on, now they didn't train it on so like, look at these numbers, 7,000 unique books versus 8 million documents. You're scaling up the training data as well. How do you scale up training data? You start going to the internet. Like, you just don't use books, which is nice, but you have to pay for it if you're a good guy. You just start, scraping the internet, but if you just scrape the internet, it's mostly crap. So what they did is, it's actually kind of nice, like nice way of finding good data for training, is they go to Reddit. And I don't know if you know, I don't know the karma points in Reddit, but it's something like, if the post in Reddit has some like thumbs up or whatever, maybe it's not that bad. It links to something which is actually worth reading or worth watching, whatever. So it's not completely spam or spam. And they filtered the links in Reddit at least with 3 karma points. So it was sort of like, oh, I want a text that somebody read and find useful, and it's not completely bullshit. I'm sorry for these words. For quality reasons, exactly. So filtering, and they get like 8 million documents. So, and just this difference, like making a bigger architecture, more layers, and making training for longer and with diverse set of documents, gave them much better results. And this is also like almost the time when OpenAI start turning from a research kind of oriented thing, like very open and paper. So GPT-1 it's a research paper. Like, no, sorry, this one is it OpenAI? I'm not sure. So this is a research paper at iClear. GPT-1 is a technical report, so it's published, but there's some details about the pre-training data, for example. You know which books, you know the architecture. For GPT-2, you still know some architecture and some documents, so you can look into that. For GPT-3, there is very few information about the pre-training data and the architecture and stuff like that. And GPT-4, it's just like, it's 90 pages for technical report, and there's just one single paragraph about the training data saying like, we just use some data. So, of course, because now, business comes into place. So, wish you good luck with your businesses, And I think this is it for today's lecture. So we're gonna be talking next time about advanced stuff, not advanced, but like more, how to fine-tune these models, how big they are, what is in-context learning, and stuff like that. Having said that, I wish you happy holidays. I'll see you January 6th-ish, something like that. January, can you look it up? January 8th. Yeah. Yeah, so like the first full week of January, I'll see you. Last year I screwed up and I thought it's vacation. I was on vacation, I thought it's holidays. And the students were here at 8 and like, saying like, oh, where's the professor? I'm not gonna do this mistake. I learned the hard way. I'm not gonna do this, this time. So I'll see you January 7-ish, something like that. Here, and having said that, thanks for attending this lecture.